Hey, my name is Josh, and I'm currently taking Physics 2212 at Georgia Tech, and this is my lab video. This lab discusses the circuits and capacitors activity. So let's go. Introduction and models. The purpose of this lab is to predict and observe the behavior of circuits and how different capacitors and resistors impact the resulting values using a voltmeter and an altimeter. Now, to achieve this purpose, we have to use several key concepts. The first being the conservation of energy, the second being Kirchhoff's circuit laws, the third being Ohm's laws, the fourth being resistance in parallel, and the fifth being capacitance. On the right, you see an example of a series circuit and a parallel circuit. Now, again, it's the same concept except formulas. V equals IR is Ohm's law, and this is a capacitance equation. We'll be using both of these later on. Now, this is an example of a model we'll be using in our experiment. Not an exact model, but an example. The system is the circuit itself, and the surroundings are, well, nothing in this example. And general overview is that the values of current, voltage, and resistance found in the experiment, they match the formulas, and in the RC circuit, the magnitude of current is time dependent. So, experimental model part 1. The first experiment that we did was a circuit with two 1.5 volt batteries, two resistors, and two amp emitters. Now, my prediction was that the current would be equal on both sides. At the R total would be 100 plus 47, as both resistors had 100 ohms and 47 ohms, which equals 147 ohms total. Now, the I equals delta V divided by R, 0.02 amps. And if it was reverse the amp emitter, it'd just be the negative of that. Now, the current amp emitter was 0.02 amps, as shown by the prediction, so that was correct. And the potential difference was 3.0 volts. And this is due to being an open circuit. Now, this is the model shown. This should be 0.20. This is an error on my fault. I forgot to change the picture, but this should be 0.20 amps. A second experiment was to replace one of the amp emitters in the previous model with a voltmeter. My prediction was that there'd be no current. If this was correct, the current was 0 and the voltage was 3.0 volts. This is the model that was used for this, and it shows that exactly. Third experiment was to close the circuit and measure potential difference across each path. Now, each path is simply B to C, C to D, and so on, as you see by these circles. How to do is we just took the volts of each one and subtracted it from final to initial, which gave these values. Now, remember these values, as we'll be using them later. Delta V round trip is all of these values added together, which equals 0 volts, and the current simply remains 0.020 amps. As you see here, these are the values. Now the experimental graph. Now this is simply the graph of the path differentials that I discussed earlier that I told you to remember. And as you see, it simply goes down to 0 as discussed and shown by the earlier mathematical results here. Now to the next experiment, connect the ammeter in parallel with the 100 ohm resistor and connect the voltmeter across the 100 ohm resistor. Now, through this, we found that the current reading is now 0.06 amps, which increased, and now the resistance is 0.96. Now, this is from the path of numbers that I discussed earlier, divided by the original current of 0.02 amps, which gave 48 ohm, and so on as you calculate it. Now, this is the model shown that was used for the previous calculations that I just discussed. Now for the experimental model, part 2. So the next experiment that we did involved a 10 ohm bulb and a 9V battery and a 200 millifarad capacitor and a 20 ohm bulb with the same battery and the same capacitor. Now when the battery was connected, the bulb lighted up and then dimmed until it eventually burned out. The current also decreased to 0 amps. When the battery was disconnected, the bulb lit up, then dimmed, and then it burned out as well. And the current also decreased to 0 amps. Now, when the 10 ohm bulb was used, the capacitor charged in 5 seconds, but discharged in 8.4. When a 20 ohm bulb was used, the capacitor charged in 15.2 seconds, but discharged in 18.9. These are the models used to calculate the previous discussed concepts. Now the experimental graph. Now we took a 9V battery, a 200 millifarad capacitor, and a 30 ohm light bulb to make this graph. We took delta V in time and we linearized delta V to make this, and we found our slope to be negative 0.247. Now we know RC is negative 1 divided by that slope, which gave us 4.045. And then RC itself is 30 ohm times 0.2 farad, which is 6 seconds. Now, there is some error here as the slope should be a different number. It should be a little bit higher. And this is probably due to me not counting time properly or missing some milliseconds on the stopwatch. Now for the discussion and conclusion. What if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? Well, if done in real life, the emitter would have resistance and or be worn down due to typical wear and tear. Thus, the current would either be increased or decreased depending on how worn and tore it was. Now, if you're doing this lab in real life and use a real battery to charge a real capacitor with no resistor in circuit, how quickly would an ideal model reach capacitor full charge? Well, if it's done on a computer, the model would reach full charge immediately, but in real life, everything has resistance, including batteries, so there would be a slow time delay. Thank you.